Now when it comes to titanium, there are different ways you can weld it. Jerry at GRB College of Welding, originally when I first took the course for titanium in February of 2013, I was not given a trailing shield. I was given a single size 8 and a size 12 ceramic cup. So a trailing shield is a luxury for welding titanium, but when it comes down to the nitty-gritty, the most basic form of welding titanium, the reason why you're giving just a single size 8 ceramic cup and a size 12 is so the welder doing the training understands about the protecting the deposited metal and the importance of the deposited metal. So if you understand if you're able to do the welding using a single ceramic cup size 8 and size 12, and all the deposited metal comes out shiny and silver, then you're adequate enough to get away with using a more luxurious device such as a trailing shield.
Yeah, so basically what I'm doing right now is if I go like this, it has an atmosphere around here. So when I come up to here, I need to purge the pipe, the distance between the pipe and the Huntington Fusion trailing shield. But yeah, shout out to Huntington Fusion. And so I'll purge the area, and I'm also purging the area with the inert gas here from the torch here, so that when I do strike an arc, there's no atmospheric gas in between my protective devices here and the weld zone.
But essentially, if I'm welding that particular technique, then what I'll do is I'll create a welding current. I'll create a weld ripple, and then I'll drop the current and protect that deposit metal away from the atmosphere. But how long of the deposit metal is protected away from the atmosphere depends on how much energy I expel to make a particular ripple. If ripples are very light energy was used to create a ripple, then get away with maybe 4 seconds maybe. If it's a lot of energy expelled, I can have them shield it for 6 seconds, 8 seconds.
Basically all the deposited metal from travel distance from 3 o'clock up to 12 o'clock is protected away from the atmosphere using this Huntington Fusion trailing shield here. And the argon from the bottle that feeds the argon to the trailing shield is less than 25 parts per million, so the weld zone and the heat effective zone will be less than 25 parts per million, so it will come out silver. And everything is protected right now, and it's allowing the everything here from the torch to the trailing shield is protecting any and all deposited metal away from the atmosphere, so it does not oxidize and form oxides. Also, I should mention that depending on the temperature that and how much energy in joules is expelled into the material, and depending on what technique I've used to with this deposition of the metal, how hot the metal is and the temperature that the metal will be at when it interacts with the atmosphere determines how long I hold the trailing shield and or individual ceramic cup on the deposited metal to protect it away from the atmosphere.
Also, an accumulation over distance. Say if I weld 8 ripples on a hot pass with a 532 filler metal, I can get away with say 8 ripples. That'd be about 150, 200 Fahrenheit, depending on how much energy I expel into the material. Each individual ripple you protect it for 8 seconds. Overall, it'll come out as silver over the whole entire stretch of maybe about 2.5 inches. But if it comes out, if you have light straw color for heat tint oxidization on the heat effective zone, if you have any oxidization in the heat effective zone, then it means that you need to, every individual ripple that you create, you protect away from the atmosphere for a couple seconds longer, another 2 seconds. And it's just an accumulation of heat over a distance. Now, when it comes to these different welding, quite often I get asked about what welding books to buy that would make a person a better welder. I know myself, I do not buy welding books. I quite often have Jerry at GRB College of Welding to go to. He essentially is my welding book. And I ask him questions, and I get tutorials, and I learn watching him weld. So I learn by asking him questions. I learn by watching Jerry weld. But one of the books that I do have that is not a welding book, but it is more of a book that teaches a person how to learn and teaches a person how to be more observant. And the book is called Neural Linguistics Programming. That's not a welding book, but that is something that you can buy. You can, whether you're a teacher, whether you teach martial arts, whether you teach welding, whether you teach grade 3 mathematics. Neural Linguistics Programming is a book that you can buy that it essentially it's a way of breaking down, say, movements. If I apply neurolinguistics to welding here, to this particular technique, then I think to myself that I need to observe and be observant of the welding technique. I need to figure out the variables. I need to break down the welding technique down to its intricate mechanical movements and components that make up the particular welding technique. And I need to figure out what both hands are doing. I need to figure out what my left hand is doing in this. At the moment, that I need to consider that the TIG torch is nothing more than just a heat source. That all it does is, on titanium, all I'm doing is I have the torch on the leading edge rather than the middle of the weld puddle. So I have the torch on the leading edge. I open a keyhole. I'm looking. My line of sight is lining up with the external. My line of sight is looking at the leading edge of the weld puddle overall, so I can see external leading edge and internal leading edge of the weld puddle. So the TIG torch is heating up the external leading edge of the weld puddle, and a split second later the internal leading edge turns to a liquid. However, the weld puddle has washed out internally. So when the internal leading edge turns to a liquid, that's when I take the tip of my filler metal and I touch the internal leading edge that is liquid. Depending on what welding technique I use, whether I use a dabbing technique or a break surface tension technique. In this video, I'm using a dabbing technique, so essentially I'm using enough current where I can open the keyhole, and I can, the keyhole, I'm carrying a liquid weld puddle, but I can, I have enough current that the energy used to expel into that, to keep that weld puddle as liquid, once I apply a solid mass, which is the filler metal, when I dab into the liquid that is the weld puddle, it in turns chills out. The weld puddle has to break down the solid mass that is being added to it. So dabbing is breaking surface tension on the filler metal's own accord, and I am dabbing material into the weld puddle, and it momentarily chills out, and I get solidification, and that overall travel over a distance. That's how you get. That's how you deposit metal over distance, is having the liquefaction of a weld puddle and the solidification of a weld puddle, and you stack your liquid weld puddle onto previously deposited metal that is solidified. And that's in all facets and forms of welding. That is essentially what welding is the liquefaction of the weld puddle and the solidification of a weld puddle. There's also the break surface tension technique, and I'm running out of time here, but there's a break surface tension technique where, rather than removing the filler metal on the filler metal's own accord and breaking surface tension between the tip of the filler metal and the weld puddle, the break surface tension technique is allowing the weld puddle to chill out and pull metal away from the filler metal. So the weld puddle breaks surface tension on the weld puddle's own accord rather than the filler metal, and that act just helps to chill out the weld puddle with the solid mass of the filler metal in place of the weld puddle.
All right, Weldtube family, there you have it. Travis did the titanium tutorial, which is super interesting to see. But we're not finished just yet. I know Travis wants to talk about something on the purging aspects of titanium. And what do you need to talk about as far as the purging wise?
Basically, it doesn't necessarily have to be titanium, but it could be any metal, stainless, duplex, nickel alloys, etc.
Okay.
Basically, essentially, when it comes to purging, and I'm going to throw out hypothetical numbers here for a purge motor. Now, this is a desktop model. It reads 999 parts per million of oxygen and less, so it's for more critical applications. But say, for example, if you have the IP65 handheld, the 100, where you could walk up to, say, you could walk out to like a 12-inch, a 28-inch, a 30-inch, like a stainless steel pipe in the shop there, and you could take little sample readings. They'll tell you what the atmosphere internally inside the pipe is. And these models are the Huntington Fusion models, are the ones I personally prefer. Say, for example, hypothetically, when you have the whole entire weld all taped up, you're going to have the very worst parts per million of oxygen internally inside the pipe. And say, for example, you have, so you're getting 50 parts per million, 60 parts per million. If you wait a little bit longer, you'll start dropping slowly, maybe 40 parts per million, 30 parts per million, but you have to wait a little bit longer. So when you start welding, you'll remove a little bit of tape at the bottom, because the bottom is going to be the very worst parts per million of oxygen. Say you get hypothetically 50 parts per million. So you're going to weld the bottom, and then you're going to, it depends on where you adjust the heat. Maybe you might weld down here and up here, over here, welding different areas of pipe while allowing a previously deposited metal to cool down. You're welding somewhere else, and also the counter pull, and also depending if it's stainless, you might counter the influence and effects of gravity and how the material sinks everything. But basically you're going to get, say, 50 parts per million or less or more, so you're going to weld a small section there, and you're just keeping everything taped up and keeping all the parts per million and the argon enclosed inside the pipe. Once you do the bottom there, then you can open a little bit more tape up here. You can weld that section. You can, and essentially as you close more and more of the root pass, the parts per million of oxygen internally inside the pipe, the atmosphere inside the pipe is going to get better and better. So when you start going on the opposing side of the pipe there, you're over half. Any deposited metal on this side is actually going to end up getting more silver and less parts per million of oxygen, so it's going to be even a better purge than the side you just welded on. A lot of the times you could take the bottle, you could flip it on the ground and roll it, and that will mix up any of the gases in the bottle and a lot of impurities that may be lighter than argon that may come out first before the argon does. So that mixes up any impurities, so that is also another trick to get very high quality purge. But essentially, as you close up more and more of the root pass and you deposit more of the root pass into the weld, you can actually get to a point where you don't even have to tape this last section, last quarter there, because the parts per million of oxygen is going to be very, very low. Exactly. Now, when you do close up the root pass, maybe you might even drop down to, say, all of 11 parts per million, 10 parts per million, etc. Very low parts per million of oxygen, because the root pass is in there. Now, when we come down to any oxidization, any heat tint on the root pass, say, for example, your root was done at, say, 30, 70 parts per million, you might have light straw color, maybe gold, yellows, browns, etc. The root pass was a certain, usually about a 1/16 of an inch on either side of the bevel. The heat affected zone is a certain width, and it's going to be done at a certain, you're going to get a certain amount of oxidization depending on how much parts per million of oxygen are internally inside the pipe when you do the root pass. When you do the hot pass, the parts per million of oxygen are going to be much better, maybe about 10 parts per million, 11 parts per million. The purge quality is going to be a lot better. And also the hot pass has a wider heat effective zone, and you're going to be heating up the root pass, including the heat effective zone of the root pass. And the heat effective zone is going to be wider on the hot pass. And because you have a wider heat effective zone than the root pass, and because the parts per million of oxygen for the root pass or for the hot pass are going to be better than what it was when you're doing the root pass, you have a good chance of having a higher quality atmosphere while doing the hot pass. So it may remove some of the heat tint that the root pass had deposited when it was at a worse parts per million of oxygen. Okay. And also, last thing is that usually when you're purging, and this is something that Jerry at JB College of Welding showed me, and this is the reason why I always go to him all the time. Quite often, I'll go in there and I'll say I'm doing a 20-inch or a 30-inch or something, or 8-inch, and I'll tell him what kind of metal I'm welding. And quite often he'll always tell me, okay, Travis, use, and he'll show me, he'll either draw it on the board or he'll actually physically show me a hose, and he'll give me charts. There's charts, say, of 2-inch, 3-inch, 4-inch, 6 and 12-inch. There's charts that show the number of hoses you use, the size of the ID of the hose that you use, and also turbulence. So say for example, say I'm doing a purge, I'm using a 1/4 inch hose, a 1/4 inch hose, 1/4 inch ID, and I set my flow rate to 30 CFH. It may be very, very turbulent, and when I do use a purge monitor, if I'm using a purge monitor in order to help with troubleshooting, I may be able to detect that my flow rate is creating a lot of turbulence and is drawing and sucking in the atmosphere and influencing my purge quality. So there's quite a lot of variables that go into purging material. Now,
the bigger the pipe, the bigger the diameter you want the hose to be?
Within reason.
Okay.
Yeah, but I'll get to that in a second. So basically, if we have a 1/4 inch hose, depending on the size of pipe, you could take a 1 foot length, say like a 1/4 inch ID hose, 1 foot length here, and just slide it over here, just tape the end off, and now you have the same 30 CFH flowing out of a larger, almost like a pigtail, 1 foot long pigtail, so the turbulence will be a lot less. Okay. You could say a 1/4 inch hose with say a 3/4 inch ID pigtail, 1 foot length hose that's taped on, and the turbulence will be even less. So on a 1/4 inch hose, it might be quite turbulent with 30 CFH, where if you have a 1/4 inch hose with say a 3/4 or 1/2 inch, then the turbulence or the flow rate may be very, very gentle. And then when it gets to say a larger diameter pipe, say if you're using one hose and you've got it maxed out to 60 because you need say 60 CFH to get to protect the inert atmosphere, and also depending on how much tape you remove, you need to replenish that amount of inert atmosphere within the pipe. So rather than having it at say you have one hose at 30 CFH, then you could use two hoses, and at 15 CFH on one hose, 15 CFH on the other hose, and it softens the flow that's coming out of the hoses. And you can also include the pigtail of a different ID hose, maybe 1 foot long, and that even makes the flow rate from a larger ID hose a lot more gentle. So these are different variables that need to be considered when it comes.
Pigtail have to be a foot long. Can I get along with just using 6 inches?
Oh, you could get any length, but preferably longer. Just so, yeah. And also it helps if you take like a steel wool, stainless steel wool, etc. And you could either put that in the hose in the end, or have it just taped on the end here. So
now steel wool is so that is steel wool. And where can you get steel wool at? You can just go on Google and Amazon and just get some steel wool?
Oh, essentially anywhere. But
anywhere.
Most common is going to be carbon steel wool, but you can get stainless steel wool, so it does not contaminate higher alloys like stainless, duplex, nickel alloys, etc.
Okay.
And essentially essentially you can take the steel wool here and you could just put it on the end there, maybe put a little bit dab of tape right there. And once the argon hits it, say if it's just like this, argon is just going to shoot straight. Yeah. Whereas if you put the steel wool in there, it's going to hit the steel wool and it's going all over the place. So you actually get it's almost like a better version of a diffuser. So it's a higher quality purge because the argon's going every which way now.
Okay. Nice. Sweet. So anything else on this, Travis? As far as anything? You explained pretty much everything, right? Now I know it's a lot to take in, so you can always rewind back and and check this out to see if what you missed. But other than that, I mean, that's pretty much the tutorial for titanium. The next tutorial is going to be aluminum, open root, correct? Yeah. 4 inch, right?
4
Schedule.
Let's get 80.
Schedule 80. Okay. No landing, right? No landing. Okay. No landing. It's going to be open root. Other than that, I appreciate everybody's support through all this time with Weldtube. I appreciate Travis for coming. We still got another video to do, but for titanium part, I appreciate you. We definitely learned a lot. Shout out to Wox for supplying us so we can bevel our titanium, and also shout out to Outlaw Leather.
Huh?
Grab the helmet. Oh, let me see. What helmet? Let me see. Oh, Travis got a little bit of helmet for. Oh, okay. I think we got some goodies for him as well. Yes, shout out to Outlaw Leather for customizing Travis. Is hood, so it has Travis Field, it has everything here. Shout out to them. Great stuff, guys. They make great work. Yeah. I know you like it, Travis, huh?
Yeah. They even color match the monkey, same purple color, everything.
That's amazing, right? Amazing.
Yeah, very high quality work. Really.
Wow. That's awesome. Yeah. Again, shout out to Outlaw Leather. Shout out to Wox. I appreciate y'all. Thank y'all. Remember, guys, burn, learn, and eventually y'all gonna earn. Y'all can subscribe, like, if y'all want to, and you can follow us on all our social medias, Instagram, Facebook, and Snapchat, all at Weldtube. And also, you can follow Travis at...
Oh, you can just type in Travis Field and
Travis Field?
I'll pop up somewhere.
Oh, he'll pop up something.
Just my name all the time. So.
Oh yeah, Travis Field, Travisfield, correct? Travis Field, and then his name will pop up first, and then you can follow him from there. Other than that, peace out. See ya. All right, cool. Now we're gonna. You can put the aluminum now.
Alright, so some companies they'll check your joules to see how much work you put into it and how many joules you put into it.
Oh yeah. What they do is they take an amp meter and a voltmeter and they'll put off some different weld procedures. They'll take also a timer, so when you start welding, they'll calculate your amperage and the voltage time, the length of time you've been welding for, and then they'll come in when you stop welding. They'll come in and measure the distance to travel. They'll do the calculation and they'll figure out how many joules. For example, I'll get you to get the calculator out. For example, if a welding procedure for super duplex is the root pass is 29,741 to 36,5, and that's what's allowed. On the 1/8 for the root pass, it's allowable from 70 to 200 amps, a voltage range of 8 to 12, and inches per minute of 1.3 to 14 inches. So say for example, I'll get you to calculate this. Say we have 90 amps times, say 9 volts times in 1 minute. And let's see, times that by 1.3 inches.
90 times 9 times 60
divided by 1.3 inches.
divided by 1.3 inches.
And that gives us 37,384. So 37,384, we're a little bit over the maximum. So essentially we have to speed up a little bit.
So you'd have an inspector or somebody come and tell you, hey, you're going too slow.
Yeah, you're going a little bit too slow. Drop it, speed up, get a little bit more distance. So take 90 times 9 times 60, try it over 1.5.
90 times 9 times 60 divided by
1.5.
1.5.
32. Okay. Now that we traveled, instead of 1.3 of an inch, we've traveled 1.5 of an inch. Same everything. We sped up our travel distance a bit. Now we got 1.5, and we have what, 32? 32.4.
Yeah, 32.
So that's how the welding procedures typically work. That's how they do welding procedures.
That would be allowable like that.
Yeah, and then when it comes to the second pass here, say for example we got the second pass of 33 to 37 joules. Sometimes they'll say they want they have the root pass at X amount of energy, and they want the hot pass at a certain percentage of that root pass, or whatever the root pass was. So sometimes you may have to slow down on the root pass, use a different technique where everything's a little bit slower, so you have less travel distance, but you have more energy expelled into the material. And then they want the hot pass to be a certain amount of joules, a certain percentage of how many joules you put into the root pass on the hot pass now.
Cool.
And the other thing I'll also mention is that a lot of these metals, they have a lower interpass temperature of say 200 degrees Fahrenheit, 150 degrees Fahrenheit, 250 degrees Fahrenheit. I forgot what I was going to say there. Oh, because the metals have a very low interpass temperature. Basically, a lot of guys will figure that they have to weld cold, but when you weld cold, what happens is that it takes a long time for the weld puddle to kind of break down the parent material you're welding on, or the previous pass you're welding on. It takes a long time to kind of break that down, get the weld puddle to move around. So essentially, that little speck that you're welding, that 1 inch, whatever, you're overheating the material trying to get that puddle to move around. So what you can do is a lot of times it's better to increase the welding current so that your weld puddle immediately washes outwards, and you can start traveling from A to B rather than in one spot stuck on a very low current and not really going anywhere but expelling a lot of energy into the material only in one spot. Yeah. I was like, oh, that's a video opportunity, I should take it.